Physicists have done the seemingly impossible, found a way to track mysterious quantum particles even when those particles aren't being directly observed. In classical physics, an object occupies only one state of being at a time. Something could be either alive or dead, for example, but not both simultaneously. But quantum physics, which seeks to explain how life works at the subatomic level, isn't so intuitive. Quantum physics differs from classical physics in that under quantum theory, objects can exist as both waves and particles, occupying both states at the same time. They only exist as either one or the other after they've been measured, as a press release from the University of Cambridge explains. Now, researchers from the University of Cambridge have shown that the movements of those particles actually can be tracked without measuring them first, by observing the way the particles interact with their surrounding environments, according to the press release. A paper describing the work was published in the scientific journal Physical Review A. Keep up with this story and more by subscribing now. Think of Schrödinger's cat, the standard paradox for illustrating this particular aspect of quantum theory. A cat in a closed box that also contains a vial of poison could be thought of as either alive or dead, so long as we can't see inside the box, as National Geographic has explained. See that the cat is not occupying both states simultaneously, but either one or the other. We need to directly observe it by looking inside the box. In this case, the researchers have created a way to track the quantum object, the cat, to determine if it's either a wave or a particle, either alive or dead, without directly observing it peeking inside the box. This premise of Schrödinger's cat, commonly referred to as the wave function, has been used more as a mathematical tool than a representation of actual quantum particles. First author David Arvidsson-Shukur, a Ph.D. student at Cambridge's Cavendish Laboratory, said in the statement, "That's why we took on the challenge of creating a way to track the secret movements of quantum particles. When any particle interacts with its environment, it leaves a tag, according to the press release. Those tags result in information being encoded into the particles." Arvidsson-Shukur and his colleagues theorized a way that physicists could map how quantum particles tag their environments without their having to look directly at the particles. Turns out, Schrödinger's cat is good for more than just abstract theory. Wave function, Arvidsson-Shukur said in the press release, is actually closely related to the actual state of the particles, so, we have been able to explore the forbidden domain of quantum mechanics, pinning down the path of quantum particles when no one is observing them. Arvidsson-Shukur said, "A spinning black hole, in an artist's rendition, illustrates a principle of general relativity that is often at odds with quantum theory." NASAD. Berry. Another hypothetical scenario used by some scientists to illustrate quantum principles is called counterfactual communication. According to Scientific American, in counterfactual communication, information can be shared between two people, often called Alice and Bob, without any particles actually traveling in the space between them. The concept is akin to telepathy, the press release explains. It's called counterfactual because the traditional facts would hold that particles would have to move between Alice and Bob in order for a message from one to reach the other. To measure this phenomenon of counterfactual communication, we need a way to pin down where the particles between Alice and Bob are when we're not looking, Arvidsson-Shukur said in the press release. Our tagging method can do just that. The researchers believe their new technique could help quantum physicists follow the movements of particles they're experimenting on throughout the whole process, even if they don't actually measure them until the very end. Save.